Good morning, dear students. Today we will discuss microwave devices, microwave sources. Devices means microwave sources, which are going to generate microwave signal. Here, the microwave signal frequency range is 1 gigahertz to 300 gigahertz. So within this frequency range, here we will study about the microwave sources that are going to generate from 1 gigahertz frequency to 100 gigahertz frequency. And moreover, microwave power is uh, it is always in watts and kilowatts power. Sometimes megawatts power also generated by the microwave devices. So coming to the generation of microwave signal. Microwave signals can be generated by using two methods, two technologies. One is microwave tubes, and the second one is semiconductor devices. Here in these microwave tubes, we will use a tube technology that is just like our triodes, tetrodes, pentodes, which uses electron beams to generate a beam of electrons. By that, to increase the power of the microwave signal, we use tube technology. And the second one is semiconductor technology. By using semiconductor technology means transfer of holes and electrons, the combination of electrons and holes by avalanche multiplication. And through the avalanche multiplication process, here we can generate microwave signal with kilowatts and watts of power. That is the second technology. Here in microwave tubes, we will study about klystrons, reflex klystron, magnetron, and traveling wave tubes. All these are going to generate microwave signal as well as going to amplify the microwave signal also. And the second technology is the diode semiconductor technology. Here, the semiconductor technology is also called as solid state microwave devices. And tunnel diode, gun diode, impact, varactor diode, spin diode, limited space charge accumulation diode, Schottky barrier diode, all these are comes under semiconductor technology. So these two types of microwave sources will generate microwave signals as well as will amplify the microwave signals up to the high level of power. And coming to the first one, microwave tubes. Here, before microwave tubes, first conventional tubes are there. Conventional tubes are triodes, tetrodes, pentodes. These conventional tubes cannot be used for the microwave frequencies because of some limitations. Because conventional tubes will be used the frequencies up to 100 megahertz only, and the frequencies above 100 megahertz we use microwave tubes. Why conventional tubes are failed at microwave frequencies? To generate microwave frequencies means the first limitation is the interelectrode capacitance. What is interelectrode capacitance? Here, conventional tube has anode, cathode. Okay, so anode and cathode. Now there is between the anode and cathode here, a gate terminal is also there. Now the distance between the anode and cathode is small, so because of that small distance, there will be a interelectrode capacitance in conventional devices, as well as the inductance of the leads. Leads means here anode and cathode are the leads. So at anode and cathode, the inductance value continuously increases. So lead inductance effect is also one of the limitation, and transit time effect. Transit time effect means here the electron takes more time to travel from cathode to anode, to reach from cathode to anode. So that is also one of the limitation, and radiation losses are also the limitations, and gain with bandwidth product is also one of the major limitation in conventional tubes. So because of these interelectrode capacitance effect, lead inductance effect, transit time effect, and gain bandwidth product limitation and radiation losses, conventional tubes cannot be used to generate microwave frequencies. Therefore, here the conventional tubes are modified as the microwave tubes by making the capacitance as a low between the leads. Now these microwave tubes, some of the points about these microwave tubes are these are used for high power as well as high frequency combination. High frequency, already we know that the frequency in gigahertz is high frequency. Uh, Generally, microwave signal frequency range is 1 gigahertz to 100 gigahertz. So within this 1 gigahertz, not 100, sorry, 300 gigahertz. So within 1 gigahertz to 300 gigahertz range, we cover super high frequencies as well as extremely high frequency bands. So this SHF and EHF bands are completely existed in microwave band. Now, so these are used to generate microwave frequencies with high power. This high power means microwave sources can generate continuous signal, continuous power as well as pulse power. Continuous power is generally used for transmission, and if you use a single antenna as a transmitter as well as for transmission as well as for reception, we use always the pulse power. So pulse power can be generated by the microwave sources, that is also high power. High pulse power can be generated. And second point is tubes generate and amplify high levels of microwave power more cheaply than the solid state devices. We have already discussed what are the solid state devices. So all these tunnel, gun diode, impact, varactor, pin diode, LSA, Schottky diode, barrier diode. So all these are solid state microwave devices, comes under solid state microwave devices. These devices specifically use the semiconductor technology, that is electron hole recombination and avalanche multiplication will provide the microwave signal as well as will amplify the microwave signal. Therefore, conventional microwave tubes are used to generate microwave signal as well as used to amplify um, the signal at the microwave frequencies to the higher levels, okay, more cheaply than the solid state devices. Then conventional tubes are modified as the microwave tubes for low capacitance, but specialized microwave tubes are also used. Okay. Then classification of these microwave tubes. Microwave tubes are classified as two types basically. One is O-type tube and the second one is M-type tube. O-type tubes are called as linear beam tubes, and M-type tubes are considered as cross-field tubes. So these linear beam tubes are based on velocity modulation process. Now, what are the linear beam tubes? Here, klystron traveling wave tubes are the examples of linear beam tubes. And so they have a focused electron beam. So this focused electron beam is going to travel through a space which is in a straight line, which the beam will travel along a straight line. Therefore, those tubes are called as linear beam tubes. Now, coming to the cross field tubes, and in cross field tubes, electron beam is also there. But the fields which are used to generate the microwave signals in these cross field tubes are always magnetic and electric fields. Those are at right angles. Here, the electric and magnetic fields in linear beam tubes uses only the electric field to generate microwave signal as well as to amplify microwave signal. So these linear beam tubes means klystrons, reflex klystrons, two cavity klystron amplifiers, traveling wave tubes. So all these are used to generate microwave signal with the help of only electric field. But coming to the magnetrons, which comes under the category of cross-field tubes. These will require two fields, magnetic as well as electric fields. Those are always right angles with each other. Linear beam tubes uses only electric fields, and cross-field tubes uses electric as well as magnetic fields, which are always at right angles with each other. Now, how the linear beam tubes will work? Here, the first example of linear beam tube is klystron. So these klystrons are considered as amplifiers as well as oscillators also. Okay, so if you use a positive feedback in the klystron, then the klystron is considered as a reflex klystron oscillator. If you are not using any feedback, that means a repeller system. If you are not using any repeller system in the structure, then the klystron is considered as an amplifier. So here in case 1, we consider this klystron as an amplifier. So that's why these klystrons are used in high power amplifiers. It means here the signal at microwave frequency means if for example, if you have an alternating signal or a sinusoidal signal at a 30 gigahertz frequency. If you want to amplify the power at 30 gigahertz frequency, you can use klystron amplifier. Okay, then so these klystron amplifiers will give the high power to that microwave frequencies. Will amplify the signal strength to the high power level of that microwave level. And electron beam moves down tube past several cavities. If you consider the structure of the klystron amplifier, there will be two cavities. There are two cavities. So within the two cavities, now the electron beam is going to move or travel between the two cavities. Okay, so because of the movement of the electron beam or traveling the electron beam, we can amplify the microwave power. Then the third point is input cavity. Already we have discussed this klystron amplifier has two cavities. One is buncher cavity and the second one is catcher cavity. Okay. Now, if you consider the cross section of the klystron amplifier, so if you observe this diagram has two cavities. This is the first cavity, second cavity. So this klystron amplifier is considered as two cavity klystron amplifier. Two cavity klystron amplifier because we have two cavities. So the first cavity, the cavity which is near to the electron gun is considered as the buncher cavity or input cavity. The cavity near to the collector is considered as a catcher cavity or output cavity. So based on the number of cavities, we consider the klystron amplifier as two cavity or four cavity or multi cavity klystron amplifier. So in this, if you have four cavities, then we call it as four cavity klystron amplifier. If you have six cavities in the structure, we call it as a six cavity klystron amplifier. So among six cavities, two cavities are considered as the input as well as output. The remaining four cavities are considered as intermediate cavities. Okay, so why we have considered a two cavity, after that four cavity, after that six cavity, eight cavity. If you increase the number of cavities, the amplification of the power amplification is also increases, and the efficiency of the klystron amplifier also increases when we increase the number of cavities. So that is the advantage of cavities. If you increase more and more cavities, then the efficiency of the klystron amplifier is also increases. Therefore, here in any radar stations, we use klystron amplifiers only to generate the microwave power, because the radar communication is completely based on the microwave frequencies. Therefore, in order to generate the microwave frequencies, we use klystrons amplifiers in radar stations. So the klystron amplifier which is used in radar station is a 6 cavity and 8 cavity klystron amplifier. Thereby, we increase the microwave frequency level up to the megawatt power, up to the kilowatts and megawatt power. Then, coming to the structure, here we call it as, here it is a klystron amplifier. So we have to apply the input signal, then the applied input signal power is amplified by this klystron amplifier. So here at this buncher cavity, we will apply the input signal which is to be amplified at microwave frequencies. The input signal applied is an AC signal at microwave frequencies with lower amplitude or lower power level. So through this input loop, we apply the input signal. Okay, so the power of that input signal has to be amplified by this klystron amplifier. So apply that input signal to the input from the input loop to the buncher cavity. Now the buncher cavity is having an alternating signal at microwave frequencies. Then coming to this electron gun, this electron gun has a cathode. Now apply cathode is going to cathode has a filament. Now apply negative DC supply, and that means the minus plus and minus sign of the negative DC supply. DC supply is connected to the cathode. Okay, cathode of the electron gun. When the negative DC is applied to the negative terminal of the DC supply is connected to the cathode, then the filament in the cathode will heat up. When the filament in the cathode is fired, then this electron gun releases a beam of electrons. So the electrons in the form of a beam is here more and more number of electrons which are in the form of a line. So that electron beam is generated by the electron gun with the help of a DC supply. So the generated electron beam is now traveling with a velocity, with a something velocity into the through a straight path, along a straight path. When the electron beam enter into the buncher cavity, it will interact with the alternating signal which is already present in the buncher cavity. Okay, so the alternating signal in the buncher cavity and the electron beam interaction is present in the buncher cavity. Now, here velocity modulation process takes place in the buncher cavity. What is the velocity modulation process? Velocity modulation process is nothing but the already electron beam is traveling with so and so velocity, with a constant velocity before entering into the buncher cavity. Once it is entered into the buncher cavity, because of the amplitude of the alternating signal, if alternating signal is having positive magnitude, then electron beam velocity increases. If the alternating signal is having negative magnitude, then the velocity of the electron beam decreases. Okay, so at the time of interaction, which magnitude is existed, so based on that magnitude of the alternating signal, the electron beam changes its velocity. Okay, so electron beam velocity changes in accordance with the